Okay, this module looks at the force-velocity relationship of a muscle, which again is a relationship that modulates the force production from a muscle. And velocity, whether you contract, that muscle is contracting at a fast rate or a slow rate, will affect force production of that muscle. This graph actually highlights another factor that modulates force production, and that is contraction type. So I encourage you to go back to those eccentric, concentric modules, and if you need some more, a refresher in eccentric and concentric. But here we have the force-velocity relationship. So velocity is along the x, force is along the y-axis. And if you notice, at 0 degrees of velocity, it's basically an isometric contraction, and velocity is 0. If you go into the positive or increased velocity, and positive we're calling the concentric direction. So if you increase velocity during a concentric contraction, the force decreases with that increase in velocity. If you go in the other direction, the negative direction, or what we're calling the eccentric direction, the relationship between force and velocity for an eccentric contraction is if you increase the velocity, there is a constant force with a slight increase in force as velocity increases, right? But it kind of flattens out. So it's not as extreme of a relationship between force and velocity concentrically, but eccentrically at high velocities, force is maintained. And that's key for any sort of follow-through activity, right? If after you pitch the ball as fast as you could, the eccentric contractions couldn't maintain a high force to slow that limb down, we would have a lot more, say, shoulder injuries than we do. So now we've seen a difference between eccentric and concentric for EMG activation, right? Eccentric is more efficient, needs less muscle activation than a concentric contraction. And in the slide previous, we saw a completely different force-velocity relationship between the two. And why is that? Okay, so for concentric, the filaments, actin and myosin, are moving past each other, right? And so as they speed up, the cross bridges just can't form. And if you decrease the number of cross bridges, you're going to decrease the force. Okay, so that's the explanation for that relationship between force and velocity and the concentric contraction. I like to think of it as if you're going through the drive-through, right? And you want to grab your coffee and donut. If you go through that drive-through at 60 miles an hour, you may not complete that cross bridge, right? You're not going to connect with your coffee and donut. It's going to stay, it's going to drop out of the car window, something. Now, if you go through that drive-through at a very slow speed, you're more likely to connect with that coffee and donut or make that cross-bridge connection. If you make those cross-bridges connect, then you will have force production. On the eccentric side, it's different. The filaments are not sliding past each other. In the eccentric, you have a minimal change in force with increased velocity. So therefore, more cross-bridges must be bound together, right? Because that's the relationship. So instead of more cross bridges forming, the hypothesis for higher forces eccentrically is that there's a decreased rate of cross bridge detachment. Now, how do we get that decreased rate of cross bridge detachment? People believe that since the cross bridges are not separating and then reattaching, they're basically being ripped apart. So it's a mechanical disruption and not based on ATP dependent detachment. So if you can think about it, if you hold your hands together and you have to rip those apart, they're going to stay connected a lot longer than if they separate and then have to reattach. A second hypothesis for why eccentric contractions can maintain that force at a very high velocity is back to Titan. That Titan adds a passive force enhancement to that type of contraction. So here's a graph that that just illustrates different points on the eccentric concentric force velocity curve. So if you're lifting 150 pounds, you can lift it quickly, right? So a fast velocity. If you increase that force, you're going to lift it much more slowly. So you're going to a lower velocity with a higher force. If you're at a certain level, and in this case it's 250 pounds, you can't move it. So there's an isometric contraction. But if you're going through the eccentric contraction or the down phase, you can generate more force at higher velocities. So you can control that contraction and you can actually lower much more weight than you can lift, even at higher velocities. So now we have this relationship between force and velocity of a muscle. And then the question becomes, what dictates the maximum velocity within the muscle, right? So how fast can that muscle contract? And the answer is it's actually determined by the fiber length. Okay, and we're going to come to that in muscle architecture, but sarcomeres end-to-end or sarcomeres in series determine the fiber length, and that fiber length determines the max velocity. So the longer fiber will have the faster maximum velocity and also a larger excursion. And another word for excursion is range of motion. So muscles like your hamstrings that have these long fibers can go through large ranges of motion and can move very quickly. And since we're mentioning velocity and force, that leads us back into power, right? Because power is also force times velocity. Peak power of a muscle occurs at an intermediate velocity. And we've mentioned that before, but we'll look at it again in a concentric contraction in the next slide. So here we have the force-velocity relationship, velocity on the x-axis, force on the y. It's as velocity increases, force decreases. This is a concentric contraction. And if we want to measure the power, it's force times velocity, and that becomes the dashed line, right? So at mid velocities, your power will peak, okay? So then that begs the question, how do you increase power? And we'll talk about different ways to increase power in the next slide. Okay, so this is a pretty busy slide, but just to orient you, so the two left graphs, top and bottom, so A and C, are force-velocity relationships, right? Concentric contractions as velocity increases, force decreases. The two right graphs, B and D, are the power related to those force-velocity relationships. And so this graph shows you what happens if you increase force, what happens to power, and what happens to power if you increase the max velocity. So let's look at A first. So at A, the lowest curve goes from around 0.5 units of force all the way up to 1 unit of force. So in this situation, think of a training situation where you've increased force production, hypertrophy, what have you. What happens to power? Power increases, but it increases at that same velocity, mid-range velocity. Okay? Now, another way to affect power is by increasing the max velocity of a muscle. So if you look at C, we increase the max velocity from about 0.5 units to about 1 unit. You can think about this as lengthening the muscle, but basically you're increasing the fiber length to increase that max velocity. And what happens to power? Power also increases, but the power increases at faster velocities. So if you want to increase the power of your athlete at faster velocities, you want to increase that fiber length. And so that's an argument for stretching, if indeed stretching does increase fiber length. Another way, how I like to think about this, is that I don't want my athlete to go from 1.0 fiber length and get shorter. So I don't want them to adaptively shorten a muscle because that would decrease the power And that peak power would occur at slower velocities.